Hi, I'm Justin Rutledge, and I will be providing a brief overview of my final project for Intro to Parallel Algorithms, a class at the University of Tennessee Chattanooga for the fall 2023 semester. I chose to do an experiment and try to design my own parallel algorithm for parallel depth first search. And I've titled this paper Random Source Parallel Depth First Search on Unweighted Undirected Graphs. And as you'll see, I have compared a parallelized version of depth first search for an arbitrary number of threads or processes to a serial version of depth first search in order to find any kind of speed up between them. And I'll go over the description of the algorithm here and then some of the motivation and methods that I've used. So as we can see here, if we have two threads that are beginning at the same time, we'll choose a random node for each of them to begin at. So here in this particular graph, we have thread 1 starting at A as its source and thread 2 starting at K as its source. Then each of them essentially perform a depth first search from there. And this particular example will have each of the progressions right-hand biased. So A goes to F, K goes to O. Each node is colored black along the way, and then each adjacent node that was not visited is put into a stack in the local scope for each thread. That will be important later. It's also colored gray, but a particular color of gray that is only available in the local scope of each thread. So we progress again through the next iteration of the depth first search, and it's worth noting that each of these threads may be traversing this graph in parallel in a different step by step, right? So they may not be at the same steps in sequence. We can't know that for sure, and so this algorithm accommodates for that. So as we see in this step, thread 1 has already visited A, F, and E. Thread 2 has visited K, O, and H, and then each of the neighbors colored gray, well, green-gray for thread 2 and blue-gray for thread 1, and their local scopes have been noted locally so that they don't put those back on their own local stacks. We continue the traversal until finally, at this step, thread 2, which is now processing node C, wants to color B gray as well, but it's already colored gray by thread 1. But that's okay. So it keeps a local note that node B is gray, and thread 1 does as well. Thread 1 continues on after traversing this local state space to node M, which it then colors black, and it does the same thing. It wants to color J and N gray, and so it does locally, but not in the global state space. In the global state space, B, J, and N they still look white to any other threads. And then finally, thread 2 moved from C to B. Since it was, and I'll go back, since it was left in the stack, it moves to B, it colors it black. Thread 1 moves from M to N and colors it black, and we'll traverse further and we'll see that thread 2 moves from B to G and thread 1 moves from M to J, because at N here, O is already colored black. It was colored black by thread 2, and black and white nodes are available in the global scope. So thread 1 has moved to J and thread 2 has colored G black. If thread 2 got to J first, it would have colored I gray with the thread 2's color, and there would be a collision to resolve, and the algorithm allows for that to occur. It's not a big deal. One of them will process that last I node first, and then both threads will at that point take a random value for a new unvisited white node somewhere else on the graph. So the entire concept behind this algorithm is that each thread processes a bit of a local state space. It only shares in common the white and black colors of the nodes, and it will take note of gray internally and then move to another random node on the graph and begin again there. So it's a non-deterministic algorithm, but it's one that could efficiently propagate through a graph under the right conditions. So I also performed an experiment. I implemented this program in C++ that would construct a graph, a very well-connected graph with several parameters here that you can adjust, like the number of threads, number of vertices, the maximum number of edges per vertex, and the maximum key value for each vertex, and then some value to find that in this particular implementation, that value to find is going to be the main operation for the algorithm. So in, say, your standard iterative depth first search algorithm, you'll have some kind of vertex operation to perform at this point after the node is colored, if you want to. I mean, if you're trying to, say, find a shortest path, there's different implementations it can be tailored to. But here in particular, this vertex operation is going to be a conditional check on whether or not the key value exists in the current node that's visited. For the random source parallel depth first search, that vertex operation occurs at a similar stage, but there's a little bit more to it. I'm not going to go into too much depth on the pseudocode or the source code, but just know that this particular implementation runs the parallel search algorithm using p-threads, and then it also runs a serial search algorithm just regularly with standard C++ all throughout. And then it will compare the times that it took to run both of them and print out the results. That's the main idea behind the program. The results that I gathered were based on 4 different configurations of parameters, as you'll see here. The number of executions for the first 3 iterations, so I basically did 10 trial runs and then compared between the serial and parallel each time. For the fourth configuration, I did kind of 2 different ones, and I broke it out into 4A and 4B. The paper gets into that, but what I want you to know in this brief introduction is that the number of vertices, the max key value, the maximum number of edges, and then the value that's searched for are what change. And we get wildly different results based on these changes. The discussion here in the results section goes over why I think that might be the case. But the conclusion that I've drawn is that in most cases, if the key value that you're looking for is easy to find, i.e. if it's highly likely to be present in a lot of vertices, then the serial depth first search is going to perform better. And I think that's because of the additional overhead required by the parallelization. Now, if say there's a 1 in a 10,000 chance of a vertex having the key value, then the parallel depth first search performs far better. And it's also worth noting that in every case where the graph is traversed in its entirety, the parallel depth first search outperforms by a significant margin. And that's about it. I've logged my whole experimental results here and everything else. So that's all that I have. Thank you.